Hello everyone, I am Dr. Osman reporting once again from the University of KwaZulu-Natal, the premier university of African scholarship. In our previous lecture, we looked at element balancing or atomic balancing and their various applications and advantages as well as some disadvantages. Today we will look at the valuable application of element balancing, especially in the fossil fuel industry, and this would include fossil fuel combustion as well as fossil fuel upgrading in order to produce high value products such as our petroleum, our gasoline, diesel, etc. Okay, so element balancing is a must to solve these fossil fuel related problems. And before that, I request that you actually go and have a look at some of the links in my description below. There are links to various videos on coal formation as well as fossil fuel combustion, oil formation and oil combustion, as well as petroleum refining. Okay, and that will put you in the picture for understanding the various applications and the value of atomic or element balancing to this industry. Okay, so watch the videos in the links in the description below, and once you're done with that, we can look at various examples and calculations using element balances. Okay, now just to move on, we will look at the applications of element balances and its value particularly to the fossil fuel industry. Okay, so fossil fuels are a mixture of macromolecules, and it is practical to use elemental analysis, including element balances. Okay, so we have a mixture of macromolecules, and this is true whether we are talking about coal or natural gas or oil. It's quite a complex mixture of many different hydrocarbons, so it's quite difficult to actually analyze the different species. So we would rather do an elemental analysis. Now there are two basic ways in which we use fossil fuels. Okay, one is for combustion to generate electricity, or for the more basic purpose of heat for warmth or even warming food for a barbecue or a braai. And another use for fossil fuels is chemical upgrading. Virtually every aspect of crude oil, gas and coal is used. It has some purpose which has been developed over the years. Okay, and this includes the conversion of our fossil fuels into usable fuels such as petroleum, diesel, jet fuel and many others such as paraffin and kerosene. Then there are other hydrocarbons from our oil or coal that can be used to make tar, as well as different polymers and plastics, gypsum and many other compounds. Now let's look at combustion. Okay, and hopefully you would have watched the videos on combustion, particularly of a coal power plant or a gas power plant to generate electricity. And we need to know how can we use element balances, or what is the need for element balances? What kind of questions do we need to ask ourselves and answer them? Okay, so in combustion there are some concerns, and the main concerns are that in combustion we want to know what should the air or oxygen feed rate be to our combustor. Okay, and this varies with different coal, and this needs to be calculated, because if we have too much of air input or oxygen input, then we will get non-ideal results, overheating, and if there is not enough oxygen, then we can potentially get undesirable products, extra greenhouse gas emissions, as well as the emissions of further pollutants that haven't been completely converted due to the low oxygen rate. Okay, so we also need to know how efficiently is the fuel being used. This also needs to be calculated. And we need to know the concentration of pollutants in our waste gas. Now this is something that can be measured and dealt with. Okay, so on points 1 and 2, we can calculate these two concerns. Now for points 1 and 2, it is useful to find the theoretical oxygen or theoretical air in order to determine the optimum air or oxygen feed rate. Okay, so let's look at our definitions. Theoretical oxygen is a calculatable stoichiometric ratio of oxidizer to fuel in order to completely burn our fuel. Okay, and it is measured in moles of oxygen per mass of fuel. Okay, so pay attention to the units of this. It's moles of oxygen per mass of fuel. Now, if the combustion plant is not using pure oxygen and instead using air, then we can work on theoretical air. And we can convert between theoretical air and theoretical oxygen by the following relationship. Okay, theoretical air is equal to theoretical O2 divided by the oxygen content of air. And the oxygen content of air, or the composition, is typically 0.21 at atmospheric conditions. Now there are of course some simplifying assumptions to this definition, and these definitions assume that all of the carbon oxidizes to CO2, all of the hydrogen oxidizes to water by the following reactions, all of the sulfur oxidizes to SO2. Okay, we also assume that nitrogen doesn't oxidize, and in cases using air, air is assumed to contain 21% O2 and 79% N2. These are fairly valid assumptions depending on whether we are actually achieving optimum combustion. Now, for example, if we do not have optimum combustion, if the feed rate is perhaps lower than what it should be, then we would have our carbon oxidizing to other things such as carbon monoxide instead of carbon dioxide. We can also form different sulfurous compounds such as H2S as well as SO3, which is far more harmful. And that's why it's so imperative that we determine what the ideal theoretical oxygen should be. Okay, so let's focus on coal. Note that the oxygen present in the coal is deducted from the total amount of oxygen required to oxidize the other fuel constituents. Okay, so in the case of coal, we do have certain compounds containing oxygen in our actual coal mixture, and this means that we could actually require less O2. Okay, because some of it can actually burn due to an oxygen being present inherently in the coal. So let's look at an example. Okay, so find the theoretical air required to burn 100 kgs of dried coal with an ultimate analysis of C being 71.2%, my S is 4.3%, hydrogen atoms are 4.8%, and oxygen being 9.5%. And one thing to note is that ultimate analysis is always done in mass composition. Okay, so ultimate analysis is a way to quantify our different elements in our fuel, in this case coal, but it can be applied to oil and gas as well. Okay, and note that coal typically has an ash content as well, which we have to take into account. Okay, so if we are looking at our ultimate analysis and we have 100 kgs of dried coal, then in mass terms, 100 kgs will contain the following masses of each element. Now in molar terms, we will have to of course divide by the molar mass of carbon, of hydrogen, of sulfur and oxygen. Okay, so in mole terms we can find our number of moles of each element. And remember that we are assuming the following reactions occur. all of the carbon must form CO2 when it's burned with oxygen, all of the sulfur will form SO2, and all of the hydrogen will form water under these reactions. So if we have, for example, 5.933 moles of carbon, then stoichiometrically we see that we will need 5.933 moles of oxygen required. Since we have 0.134 moles of sulfur in our coal, we will need stoichiometrically 0.134 moles of oxygen. And we have stoichiometrically 4.8 moles of hydrogen in our coal. Stoichiometrically we will need a quarter of that, so that's 1.2 moles of oxygen. So this is the amount of oxygen that's needed as per these reactions. But what we also mustn't neglect is that our coal already has some oxygen in it, so we have to subtract that. So we have 0.594 moles of oxygen already present in our coal, and this is moles of oxygen, right, elemental oxygen. So our moles of oxygen gas is half of that, right? That's our moles of O2. So our theoretical O2 required is our summation here, subtracting our oxygen or equivalent oxygen gas in the coal. So that's my theoretical oxygen. And to get my theoretical air, I can simply use the relationship between theoretical air and theoretical O2, and that ultimately equates to 6.970 divided by 0.21. Remember, we are assuming 21% oxygen in atmospheric in air, and that leaves us with 33.19 moles of air per 100 kgs of coal. Okay, and that's the problem solved. In practice, more air is typically introduced than is needed, and this is to compensate for ineffective mixing. However, we can't just introduce a large excess of air as much as we want. So it's important to know the excess because it ideally should be minimized. We don't want too much of excess. Okay, so here's the consequences of deviating from the theoretical air or theoretical oxygen. If we input too little air, it results in incomplete combustion. However, if we have too much of air or a very high excess, then it makes the combustion too violent and difficult to control. And also it's difficult for the effective harnessing of that heat. Remember, our combustion must generate heat, and that heat is typically used to heat up water to generate steam, and it's the steam that drives our turbines. However, if there's too much of heat, then there's not enough water to actually capture that heat and turn into steam in order to drive our turbines, so some of that heat ends up getting wasted. Okay, so if we have too much air and we have violent combustion, then our heat ends up getting lost through the stack and gets emitted. Okay, so we can define our percentage excess air being the moles of air supplied minus the theoretical air divided by the theoretical air, and we can multiply by 100 to get our percentage. Okay, now let's look at another example, and this is pertaining to syngas rather than coal. However, it is the same principle. We can also use gas for our combustion to generate electricity. So syngas is typically a mixture of carbon monoxide and H2 produced by methane reforming. Okay, it is a synthesis gas. It's not the same as natural gas. Okay, natural gas is typically a mixture of many hydrocarbons. So this is syngas, and our syngas can be burned as a feedstock, or it can be used for organic synthesis. In other words, chemical upgrading to produce different products such as polymers. Okay, so in this example, the syngas is being burned. Okay, and we have a combustor. And this is the composition of my syngas. Okay, it has some methane, of course, left over from the methane reforming, which is not completely perfect. And we have a large amount of hydrogen and carbon monoxide, and some small amounts of CO2 as well as oxygen and nitrogen. And that's going into a combustor, and we are putting in air as well. We are feeding air to this combustor, and we are ultimately getting a flue gas coming out, consisting mainly of CO2, H2O, oxygen and nitrogen gas. So let's look at our element balance. Okay, and remember that before we do any element balance, we have to check whether our balances will be independent. And also another piece of information is that syngas is burned in 10% excess air. And we want to know what the flue gas composition is. Okay, so here's my matrix of elements for each of my different species associated with this combustor. And as you can see, if we do a Gaussian reduction, we will end up with all of our element balances being independent. Okay, so now once we've established our element balance independence, then we can draw up our degree of freedom table. Okay, and here's my degree of freedom table. Let's count the number of independent variables. Remember that although this is a combustor, we don't really know what the reactions are, and we are conducting an element balance, so we don't have to worry about that either. So our number of independent variables are as follows. We count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so that's 12 independent variables. There are a maximum of 4 elements associated with this combustor. So my number of independent balances is 4. And now let's look at my number of independent specifications. We have 1, 2, 3, 4, 5, and nothing else. So that's it. So it's just 5 independent specified compositions. And we have been given a subsidiary relation, two subsidiary relations. One is that we are given our percentage of excess air, which is a valuable piece of information. And also we are given an air ratio. Remember that we are assuming that our air contains 21% oxygen and the rest being nitrogen. Okay, so that's our assumption. And based on that, we can ultimately end up with a degree of freedom of 1. And if we add in a basis for our syngas, then that will make our degree of freedom of 0. So let's look at it. We have a basis of 1000 moles per hour of syngas. Okay, this is just arbitrary. We could have chosen 100 moles per hour or 10,000 moles per hour, but we can just choose 1000 for now. So let's look at the composition of our carbon, hydrogen and oxygen in our syngas. So looking at our number of carbon atoms, the number of the moles of carbon in stream 1 include my moles of carbon in CH4, which is 0.004 times N1. Okay, there's no carbon in H2. There is 1 mole of carbon in CO. So that's 1 multiplied by 0.383 multiplied by 1000. There's also carbon in CO2, okay, at 5.5%. 1 carbon for 1 mole of CO2, so that's 1 multiplied by 0.055 times 1000. Okay, so that's my moles of carbon in the syngas. We can perform the same for the moles of hydrogen in stream 1. Okay, so there's 4 moles of hydrogen in 1 mole of methane. Okay, so that's 4 multiplied by 0.004 times 1000. Okay, so that's it over there. There's also 2 moles of hydrogen in 1 mole of hydrogen gas. So that will be 2 multiplied by 0.528 times 1000. So the addition adds up here. And now we can look at the moles of oxygen in our syngas. Okay, there's no moles of oxygen here or here. However, there is 1 mole of oxygen in CO and 2 moles of oxygen in CO2. Okay, and there it is here. So 1 multiplied by 0.383 times 1000 plus 2 multiplied by 0.055 times 1000. So this is for the CO and this is for the CO2. Okay, and in addition to that, we have 2 moles of oxygen in oxygen gas. And there it is here, 2 multiplied by 0.001 times 1000. And this is the summation. Okay, and remember that we can assume the following reactions. All of the carbon becomes CO2, the hydrogen becomes H2O. There is no sulfur here, so we don't have to worry about the reaction with sulfur. So let's look at our theoretical oxygen. Okay, since I have 442 moles of carbon, I will need stoichiometrically 442 moles of oxygen gas. So that's that over here. Since I have 1072 moles of hydrogen, I will need a quarter of that for oxygen. So that's 1072 divided by 4. And since I have 495 moles of oxygen already present in the syngas, that equates to 495 divided by 2 of oxygen gas molecules. So my theoretical oxygen gas is 442 plus the following, subtracting the oxygen already present in the syngas. So that's 462. So I can calculate my theoretical air to be 462.5 over 0.21. So that's my theoretical air. And remember that we have a 10% excess air. So here it is here. 0.1 is equal to my air supplied minus my theoretical air divided by my theoretical air. So now I know what my air supplied is. Okay, and here it is here. So for 1000 moles per hour of syngas, taking into account the theoretical air and the excess, we will need for stream 2 the following moles of oxygen gas and nitrogen gas. So once we know what's present in stream 1 and we know the amount of air coming in at stream 2, we can now proceed with doing an element balance in order to obtain the composition here of stream 3. So here are my element balances, and let's look at it for nitrogen. Okay, Okay, so we have our moles of nitrogen here, and that should be equal to our moles of nitrogen here plus our moles of nitrogen in the syngas. So I have 2 multiplied by N3 of N2. Okay, here it is here. Subtracting the nitrogen in the air. So that's 2 multiplied by N of N2 in stream 2, and subtracting 2 of N1 of nitrogen. Okay, so here it is. And of course it's equal to 0. My elements are always conserved. And we know what these values are here. The amount of nitrogen in stream 2 as well as in stream 1. So we can get our amount of nitrogen in stream 3 quite easily. In terms of our hydrogen, we do the same thing. We have our hydrogen coming out in the form of water, and that is equal to our hydrogen coming in. And that is in terms of our methane and our hydrogen gas. So 2 multiplied by N3 of H2O minus 4 multiplied by N1 of CH4 minus 2 of N1 of H2. Okay, and here is the expression. Okay, I encourage you to do this on your own just to confirm. And since we know what N1 is, we can ultimately obtain N3 of H2O. And the same for carbon. We have all of our carbon coming in the form of CO2. So N3 of CO2 minus our carbon coming in stream 1 in the form of CH4, CO, and CO2. And here it is here. And we already know what these are. So we can easily find out our amount of CO2 coming out at stream 3. And finally, the oxygen is perhaps the most complicated because it's prevalent in so many different compounds in CO2, H2O, and oxygen gas, as well as in the air, the theoretical air, the air input, and in the many different compounds of the syngas. So let's count the oxygen in stream 3. So that will be 2 times N3 of CO2 plus 1 times N3 of H2O plus 2 times N3 of oxygen gas. Okay, so here it is. Subtracting my inputs, that is 2 of N2 of oxygen gas, and of course subtracting 1 of N1 of CO2, CO, minus 2 times N1 of CO2 minus 2 times N1 of O2. Okay, so here is the subtracting stream 2 and stream 1 components. And ultimately we can sequentially obtain our moles of oxygen gas in stream 3. Now that we have each of our flow rates, it's quite trivial to obtain our composition. Okay, and that's the problem solved. Okay, finally, just a re-emphasis on the importance of air regulation in fossil fuel combustion. Okay, recall that if we have too little oxygen supplied, and then we of course will get incomplete combustion, and that will result in many gas emissions and polluting issues. We will have the formation of carbon monoxide rather than carbon dioxide. CO, as you know, is a harmful pollutant, And we also get black smoke being emitted out the stack, which is elemental carbon or soot. Okay, and we get this as opposed to getting ash being emitted out through the stack. And on the other hand, if we have too much of oxygen supplied to our combustor, then we have violent combustion, and we are often unable to harness the amount of heat generated by this excess combustion. So heat is therefore lost at the stack. So ideally we should have complete combustion producing high amounts of CO2 or maximized amounts of CO2, as well as no or minimal carbon monoxide and minimal heat loss at the stack. Oxygen, of course, should also be zero or minimized in the flue gas. Okay, so this is just a diagram to illustrate, okay, when we have not enough oxygen, or in other words, our actual air is a lot lower than our theoretical air, then we have the formation of carbon monoxide out at the stack. We have also, of course, no oxygen because all of the oxygen is being used up because we have so little air. And we have CO2 being produced initially at comparatively low quantities. Now, as we increase our actual air and bring it closer to theoretical air, we reach the following zone. Okay, so this is where our actual air is equal to our theoretical air. And we enter this zone here, which is the optimum oxygen excess zone. Okay, remember that it's quite difficult to obtain this value of 1 for actual air and theoretical air. And also, by inputting our actual air, we actually do not achieve what the theoretical results would be due to incomplete mixing. Therefore, we need to have a bit of excess oxygen coming in. Okay, and we note that in this range, we have minimal heat losses. Okay, whereas previously we had high heat losses. And we have, of course, as we have more and more excess, we will have more and more oxygen coming out through the stack. We also have very minimal to no CO being formed. And we have a maximum of CO2 or carbon dioxide being formed. And note that as we go beyond this, our stack heat losses increase. Our amount of oxygen, of course, would increase, and our amount of CO2 decreases. Okay, so just a few more notes here. Now, the lower the flue gas temperature, the lower the heat at the stack. Okay, so we ideally want our flue gas temperature to be as low as possible, which means that there will be hardly any heat lost through our stack. Most of the heat will be captured in the combustor. So that points to a high combustion efficiency. Now we can have a generalized formula here for any kind of fuel, provided we know the formula of the fuel. So for complete combustion of any fuel, and if we know its formula, then we can assume the following equation. Okay, so let's say our fuel has the typical elements C, H, O, and S, and the following atomic numbers in the actual molecule of X, Y, Z, and W. And we have the following oxygen stoichiometric ratio, and it would produce the following products. Okay, where we have our X, Y over 2, and W here. Okay, and this formula is quite useful for most coals. However, it ignores other trace elements which might be within the ore as well. And this will, of course, give us the theoretical amount of oxygen required. Okay, in terms of volume at 1 bar and 298 Kelvin. Okay, so we can calculate it here. Our meter cubed of O2 per kg of fuel is 24.45. That's our volume at ideal gas conditions. And we use the following formula here, where these are the molar masses of CHO and S. Sorry, this is 16 here. Okay, so these are the decimal weight of elements on a dry mass basis in 1 kg of fuel. Okay, for those of you who are taking the mass and energy balance courses, it's useful to refer to example 3.10 in your notes. Okay, now that we've discussed a fair bit about fossil fuel combustion, let's look at chemical upgrading more closely and look at an example, as well as how element balancing actually applies to chemical upgrading as well. Okay, so our fossil fuels, namely oil, coal and gas, can also be upgraded to many useful fuels such as petroleum, diesel, jet fuel, paraffin as well as kerosene. And the purification of our fossil fuels in order to obtain this involves some heavy metal removal as well as sulfur removal. Additional products include tar, polymers and gypsum or plaster of Paris. Chemical upgrading is usually achieved by a pyrolysis process, so a very high temperature process involving the thermal decomposition of carbonaceous material. And this also results in the production of methane, tar and coke, which have various uses. Pyrolysis is a broad term for a very complicated process involving catalytic reforming, vis breaking as well as coking and thermal cracking. Once pyrolysis is done, chemical upgrading also requires hydrogenation. And this involves adding hydrogen to carbon, and it can be used to convert coal to oil or gas in order for it to be processed to produce our useful fuels. It also results in methane production, which is also a precursor to convert to various useful fuels. And thereafter, it also involves the removal of impurities such as our nitrogenous material, our oxygen, sulfurous material, chlorides from our fossil fuels. And it results in easy removal and therefore pollution prevention, particularly air pollution prevention. However, this is a very energy intensive process, so we have to spend a very vast amount of energy in order to actually produce our useful fuels. Now let's look at a fairly elaborate example. We have our dry pulverized bituminous coal, and we ultimately want to put it through a pyrolysis plant in order to produce synthetic crude oil. And we can ultimately use this synthetic crude oil in order to produce various products such as petroleum and diesel and also paraffin. So let's look at this process. We have a two-stage pyrolysis. So we have dry bituminous coal with the following ultimate analysis. Remember, ultimate analysis is in weight percent. And it's contacted with a hot synthesis gas over here to produce raw coal oil. As well as a high methane content gas, which is the gas here, and some char. Now the high methane content gas has a dry basis analysis of the following. So this is a mole percent dry basis. In other words, these are not the actual compositions but rather the dry compositions, the compositions that are excluding the water. So you must be very careful about that. And the gas is found to contain 48 moles of H2O per 100 moles of water-free gas. So we have the following: 48 moles of H2O per mole of water-free gas. Okay, so that's a subsidiary relation. A bit tricky to interpret, but we've done it here. And we are also given the raw coal oil ultimate analysis as follows for carbon, hydrogen, oxygen and sulfur content. Now 150 kgs of raw oil is produced from 1000 kgs of dry coal. Okay, so F3 over F1 is 150 divided by 1000, and the char from the first pyrolysis stage is transferred to a second stage, that's that over here, in which it is gasified with steam. Okay, so we have a steam input and oxygen to produce the hot synthesis gas for the first stage. Okay, so our pyrolysis stage 2 is simply to produce synthesis gas to feed into pyrolysis stage 1. Okay, and we have the composition of the synthesis gas, and this is by mole percent. Okay, so currently we have this in mole percent as well as our stream 2 in dry mole percent. We have our coal in mass percent, ultimate analysis, and our raw coal oil in mass percent. Okay, so we have our composition, and our synthesis gas is being produced, as well as our char, which is essentially elemental fixed carbon as well as ash. Now the raw product gas from the first stage is sent to a purification system, okay, to remove our CO2, H2S, as well as some water, and the result is a gas consisting of 15 mole percent of methane and CO2, as well as CO2 and H2 in a 1:3 mole ratio. Okay, so we have our product gas here, and it is split off. This is a splitter, and so we have the following compositions which will apply to stream 14 and stream 11. And this particular composition is suitable for methanation. So we split a larger portion to a hydrotreating plant, and in the hydrotreating plant the raw coal oil is subjected to a mild hydrogenation. Okay, so we have a mild hydrogenation using the recycled product gas and some makeup from our hydrogen gas to produce a synthetic crude oil consisting of 87.5% carbon, as well as some hydrogen and a very small amount of sulfur. Now the hydrotreating increases the hydrogen content of the oil using the recycled product gas and some makeup hydrogen to produce a synthetic crude oil. Okay, and hydrotreating increases the hydrogen content of the oil by removing oxygen and sulfur from our raw coal oil, and the off gases from the hydrotreating system will also be sent to the purification system. Okay, and we are given the composition of H2S as well as the mole ratios of our our H2 to water as well as our CO to water. Okay, and our task at hand is to find the flow rates of each stream in this process. Okay, so we are given lots of information. This is quite a large process, so we can expect this to be very tedious. And we are also not given the reactions for our pyrolysis stage 1 and 2 or our hydrotreating system. So it is by default that we have to use element balances to solve this problem. Now, in order to use element balancing, we have to first check for our independence of our element balances, and we can do this for C, H, O, and S in each unit, and by looking at our various species. Okay, and this hasn't been done here, so I encourage you to confirm the element independence as homework for each of these systems. But for now, I can assure you that for each process, our element balances will be independent. Okay, so let's look at our degree of freedom analysis, and we can count for our pyrolysis process firstly. So let's look at pyrolysis stage 1. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23 variables. Okay, remember that we don't know what the reactions are, so we can't count any reaction rate variables. So it's simply our stream variables. In terms of our number of balances, we have 4 element balances plus an ash balance, which we can choose to include. And we have the following specified compositions, independent compositions. So we have 5 here, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yes, okay, and that's excluding ash, so that's 15 there. As follows. And we have one subsidiary relation, our dry gas ratio, our water to dry gas ratio, so we can include that. And that ultimately gives us a degree of freedom of 1. Okay, and I can count for my pyrolysis 2. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 variables, 4 balances. Okay, there's no sulfur at all in this particular unit, so it's simply our 3 elements plus our ash, so that makes it 4. And we have some specified compositions, 4 independent compositions specified, and that gives us a degree of freedom of 4. If we look at our hydro treating, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so that's 16. Again, 4 elements, so 4 balances, and we have some specified compositions as well as 2 subsidiary relations, and that gives us a degree of freedom of 3. In terms of our purification system, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so that's our 17 there. And this is another interesting point which I'll get to, but for now let's look at our balances. We have a maximum of 4 elements, so 4 element balances, 6 specified compositions, and the following subsidiary relations, and that gives us a degree of freedom of 4. And now we can easily look at our splitter. That's perhaps the easiest unit of them all in this process. 9 variables with our splitter restrictions, 3 balances because there's 3 different elements. And for our process, we count for every stream, so it adds up to 48. I encourage you to check this. We can add up our balances to 20. and take note of all of our specified compositions and subsidiary relations. And initially we end up with a process degree of freedom of 3. And remember, for our overall balance, we take into account only our outer streams. Okay, so we can count here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and 19. So that's our 19 there. 4 elements plus an ash balance, so that's 5, and some specified compositions and a split ratio. Okay, that gives us a degree of freedom of 6. Now currently, the way we see it, we can't really solve this process because we have a process degree of freedom of 3, which is very high. However, we can actually squeeze out more balances if we choose to actually use species balances in addition to our element balances. Okay, so we can perform a species balance on any 2 of our components, and that will add on balances here, for example for our purification system, and that will ultimately add on 2 more balances to the process, and that will bring it down to 1. And thereafter simply adding a basis, and we can get our degree of freedom to be 0. And remember that if we add our basis to the pyrolysis stage 1, then in particular we have our degree of freedom for our pyrolysis becoming 0. Note that if we stuck completely with only element balances, we won't be able to solve everything. Okay, so we have to use species balances, and we are using it for the purification system in particular because our purification system is a non-reacting system. Okay, so now applying a basis, and that will give us a degree of freedom of 0 for pyrolysis 1. So we can state that for stream 1, for example, we can let that equal to 1000. Okay, and that's 1000 kgs per hour. Remember, this is in mass flows now. And once we determine that, then we can write out our balancing. Okay, so we need to know our molar masses for C, H, O, and S in order to perform a molar balance, ultimately with the intention of doing an element balance. Okay, so let's look at our balances. Our ash balance is the simplest. We have ash coming in at stream 1 and all of it leaves out through stream 4. Okay, so that's my input minus output is equal to 0. So that is my mass flow rate of ash in stream 4. Now let's look at our sulfur balance. So we have sulfur coming in here, about 350 kgs per hour. And we also, okay, we don't have any sulfur coming in here, so this is the only input. Okay, so that's my output minus my input, and that's equal to 0. And let's look at my output. So we have an output in stream 3. So that's the sulfur there, 2% of stream 3 in mass terms. And then we have sulfur coming out in stream 2. in the form of H2S and 1 mole of sulfur in 1 mole of H2S, so that stays the same at 4%, multiplied by the dry molar flow rate multiplied by the molar mass of sulfur to maintain our mass balance. Okay, and this is subtracting our input. Okay, so that's 35. And ultimately we can just reduce it as follows and find out what N2 dry is. Okay, so this is the molar flow rate of all of these components, excluding the water. Let's look at our oxygen balance. Let's take note of all of our outputs. We have an oxygen output here, so that's 0.08 multiplied by F3. We have oxygen in CO as well as CO2 and H2O. So that's 18% of N2 dry, as well as twice times 25% of N2 dry. So there's my 18%, there's 2 times 0.25, and also 1 multiplied by the molar flow rate of water in stream 2, which we currently don't know. Okay, and that's multiplied by 16, our molar mass of oxygen. Subtracting all of our inputs, we have inputs in stream 5 with CO, CO2 and H2O, 1 mole of oxygen in CO, 2 moles of oxygen in CO2, and 1 mole of oxygen in water. Okay, so here it is. So that's 12% of N5, that's representing the CO. This represents the CO2 twice because we have 2 moles of oxygen in CO2. And we have 42% of N5, so that's representing our water, the oxygen in the water. And we of course need to subtract our oxygen input in our dry coal. Okay, so that's inherently in our coal. Now let's look at our carbon balance. We have carbon all over the place here, so we have to be very thorough about this. So looking at our outputs, we have 82% of F3, and we have carbon in stream 2 in the following as percentages of N2 dry. We also have elemental carbon as an output in stream 4, and we have 2 inputs. Okay, so here's all of our outputs, and we have 2 input streams. We have carbon coming in, so that's 72.5% of the flow rate of stream 1. And we have carbon in CH4, CO and CO2. So this represents the stream 5, and that's my balance. And finally, we look at our hydrogen. We also have a high occurrence of hydrogen, so our outputs, we have 8% of F3, and we have 4 moles of hydrogen in CH4, 2 moles of hydrogen in H2, 2 moles of hydrogen in H2S, and 2 moles of hydrogen in water. Okay, so here are my terms here. That's my outputs for stream 2. We also have elemental hydrogen coming out. And of course, 8% of F3. Remember, F3 is 150 due to this ratio here. And our inputs, we have an input of stream 5, okay, our CH4, H2O and H2, and we have elemental hydrogen in the coal. Okay, and writing out these balances, we can then solve for N2 dry and thereafter the molar flow rate of water in stream 2. From our oxygen balance, we can solve for the entire N5. We've solved for our ash balance quite early in the balance. And from our carbon balance, we can solve sequentially for the carbon and hydrogen in stream 4. So ultimately, we can solve all of our species flow rates and compositions surrounding pyrolysis stage 1. Okay, and that's the pyrolysis stage 1 solved. And we can also move on to pyrolysis stage 2, and thereafter the purification, the hydrotreating, and finally the splitter. And I encourage you to complete this as homework. For our particular pyrolysis stage 1, we simply wrote out our balances, and it was quite simple enough to solve our balances sequentially. However, for pyrolysis stage 2 and our hydrotreating, we may find that we will need to actually solve our balances simultaneously, in which case we can simply put it in a matrix and solve for all of our unknowns. Okay, and that will be the problem solved. Okay, so I encourage you to complete this as homework.